Welcome to Ask and Learn.
So we have a capacitor with two plates. That looks like this. And then we stick a dielectric in here. So this is L, and it's also, it goes back like this, so it's also L. And then this is separation of D, and this goes in X. This is the dielectric material. So first we want to find the capacitance. So this is basically, we have two sections here. There's one with the dielectric and one with just air. And that's really just two capacitors in parallel between the two plates. So I'll call this one with the dielectric C1. And that's going to be kappa times the area of that dielectric times epsilon naught over D. And then C2 is going to be the capacitor with just air filled, not with the dielectric. And that'll be that area times epsilon naught over D. So the area for the dielectric is pretty easy. It's just, well, it's going to be L deep and X wide. And then for the air-filled capacitor, it's also L deep, but then wide, it's not X, it's L minus X, because it's this dimension right here, which is L minus X. And then times epsilon naught over D. And since they're in parallel, we can just add the two together. So the equivalent capacitance is going to be C1 plus C2, which is kappa Lx epsilon naught over D plus L times L minus X times epsilon naught over D. So now we can factor out, let's see, L, epsilon naught, and D. So we get epsilon naught L over D times kappa X plus, this is going to be L minus X. We can factor it even a little bit more. So we have two terms with an X in them. So first of all, there's an L, and then we have a kappa times X and a minus 1. So that's X times, this should be plus X times kappa minus 1. So this is the equivalent capacitance. Now the energy stored, I'm going to do it in terms of capacitance and voltage, because those are the values we're given, at least the voltage. So this is going to be 1/2 times epsilon naught L over D times L plus X times kappa minus 1 times delta V squared. Okay, now we want to find the force, and I'm going to do it as a force vector because we want the magnitude and the direction. So that's going to be minus du dx in the x direction, so I hat. So this is positive x, that direction. So this is going to be minus d by dx of 1/2 epsilon naught L over D times L plus X times kappa minus 1 delta V squared I hat. So we can take out all the constants first of all. So this is minus 1/2. This should be there. So delta V squared epsilon naught L over D. And then now we're taking d by dx of L plus X times kappa minus 1. So that's going to be, if we take the derivative of this, well, the L goes away, the X becomes 1, so we get just a kappa minus 1. So This is our force. And now we're given L equals 5 centimeters, and X equals L over 2, so that's 2.5 centimeters. Kappa, the dielectric constant, is 4.5 for glass. And our potential is 2 times 10 cubed volts. So now let's plug in these numbers. We're going to get minus 1/2 times 2 times 10 cubed. And then we have epsilon naught is 8.85 times 10 to the minus 12. L is 5 centimeters, but we want that in meters, so that's going to be 0.05 meters. Same thing with D. Oh, I didn't write that down. D is 2 millimeters, which is 0.002 meters. So that's 0.002 meters. And then we want kappa minus 1, so 4.5 minus 1. And this comes out to minus 1.55 times 10 to the minus 3 newtons. And the minus signifies it's in the minus x direction. So minus 1.55 is going to be, that's the force.